Here we see a stretch of the Milky Way on a fisheye lens, it looks like, from northern Chile. This is from the VLT Observatory, and you see our view of the Milky Way galaxy, our flat galaxy stretched across the sky. So how do we know, since we live inside our galaxy, what it's like? Well, the first person to make a serious attempt at learning about the size and shape of our Milky Way galaxy was the great astronomer William Herschel, the greatest astronomer of the 1700s, almost without argument. And he did it simply by a star count. He started counting stars in every direction of the sky. And at the bottom here, you see his attempt, which is pretty amazing with the technology he had, that just counting stars so meticulously. Now, the one thing that he got right, he shows a fairly flat galaxy, which is great, which is correct. But he has our sun, that yellow dot, somewhere towards the center. So he was off on that, but of course that's not his fault. He didn't realize he wasn't seeing nearly all of the galaxy. In the last section we learned that what you're really looking at when you see the Milky Way in the sky is the next arm over. You're not seeing all the way to the center. Anyway, it was an amazing job by William Herschel to at least show that we live in a flat galaxy. This is kind of the latest view of what we think the Milky Way looks like. And the one big change that's happened in the last 10, 15 years is this middle section here is now considered to be a bar. So we now think it's a barred spiral, not just a regular spiral galaxy, but a barred spiral. And you see we have several arms coming out, and we live on a little arm called the Orion Arm, or the local arm. And again, we're out here in the suburbs, if you think of the spiral arms like suburbs. Here you see the Milky Way across from the Grand Teton Mountains there. And our location, if you shrunk down the Milky Way to the size of North America, we would actually be, let me bring that back real quick, we would be somewhere floating above Buffalo, New York, and just a little bit above the plane, maybe 15 miles above the plane in Buffalo, New York. Again, if it was based, the center of the galaxy somewhere here in the Midwest, and we would be somewhere up in here. Okay. So how do we know nowadays how big the galaxy is and so forth? Well, they noticed back in the day, hundreds of years ago, that what they called spiral nebulae, which we know are other galaxies, and globular clusters, which are those big clusters, spherical clusters of stars that orbit our Milky Way, they were just too far away for parallax shift. But they have an abundant number of blinking stars. When we say variable stars, we mean their brightness changes. RR Lyrae, and Cepheids. The RR Lyrae blink faster. They have a period of 1 day or less, so they're actually blinking brighter and dimmer every single day. But they're very consistent. All of them act the same. Whereas a Cepheid variable, well, it depends on which Cepheid you're looking at. Some of them may blink quickly in a day, some of them a week, some of them a month or more before they actually kind of blink. So Cepheids are a little harder to study because of that variety. But they do have an advantage over the RR Lyrae, and the advantage is they're brighter. So Cepheids are brighter, which means we can see them farther away. So they're a little more complicated to deal with. But I like to give this analogy. The RR Lyrae are kind of like little refrigerator light bulbs, okay? But they're all exactly the same. There's a standard RR Lyrae star, and they're actually found in globular clusters. So that would be probably their main use, is finding the distance to globular clusters. But when it comes time to measure distances to other galaxies, you need something brighter, and that's where the Cepheids come in. Now, the good news about the Cepheids is if it has a period of 20 days or 30 days or 40 days, at least that particular star is very constant. Okay, it will blink every, 45 days like clockwork. And that's going to allow us to measure distances. I'll get to that in a moment. Here we see a graph of an RR Lyrae with a very short period of about half a day. And then here is a Cepheid, which still has a fairly fast period of every, looks like maybe 3 days or so for the period for that one, which for a Cepheid is pretty short. Anyway, Sir Arthur Eddington, the guy that studied the eclipse in Africa to help prove Einstein, he figured out that these stars are simply unstable. They're towards the end of their life, and they are actually swelling up and shrinking down, and that's why they're getting brighter and dimmer, because their size is changing. They're unstable. But the great news is they have that constant period, and so we can actually calculate their luminosity based on how often they blink. I'll get to that more in just a second. But we can use them essentially as standard candles. We know their brightness. Okay, both the RR Lyraes and the Cepheids are standard candles. We know their brightness, and therefore we can use the good old inverse square law. That's where you take, let's say, two light bulbs that are the same brightness. You move one twice as far away, it's 1/4 as bright. Move it 3 times farther, it's 1/9 as bright. The RR Lyraes and the Cepheids behave exactly the same way. Now, here's an important graph that shows this. The RR Lyraes are all down here, which means they're not very bright. Those are like our refrigerator light bulbs. But at least they're all the same. They're not hard to work with, because if you've seen one, you've seen them all. But fortunately, the Cepheids, which have a much greater variety in both their period and their brightness, the good news, look at that, they fit right on that line. So all you have to do to know the brightness, the luminosity of a Cepheid, is to see how often it blinks. So for example, looking at the graph, if it blinks every couple days, you come up to the graph, and that tells you the luminosity is somewhere over here. Okay? Whereas if it blinks every 20-something days, you come up, and now it has a luminosity of 10,000. So you can match the blink to the brightness. The person that figured this out, actually, was Henrietta Leavitt and her team at Harvard. Those were the ladies that they called computers at Harvard, and this was a really big discovery. Annie Jump Cannon and her team, which included Henrietta Leavitt. So the RR Lyraes are all about 100 times the luminosity of our sun, okay, which is still awfully bright, but the Cepheids are even brighter. They just vary depending on distance. So to recap for the Cepheids, the ones that blink the fastest are the dimmest, and the ones that take a long time to blink are brighter. And those are so important because they can be seen in nearby galaxies. And that's what first allowed us to measure the distance to other galaxies. That's how we knew they were other galaxies. Up until that time, they were calling them spiral nebulae. They thought they were clouds within our own galaxy. But thanks to Cepheid variables and the work of a guy named Edwin Hubble, we found out that they were actually located in other galaxies. That was huge. That was a huge moment in astronomy and science. And the universe became a whole lot bigger when we realized that. So this brings us to the distance ladder. This gives us a new rung on what's called the distance ladder. Right here in our neighborhood of the solar system, we can just use radar to measure distances. Going out to nearby stars, you can use stellar parallax. Remember the parallax shift. As the Earth goes around the sun, the stars seem to shift. But unfortunately, the parallax shift gets smaller as you get farther away. So how do you measure distances across our galaxy and even to other galaxies? Well, that's where the variable stars come in. So the RR Lyraes are good within our galaxy to measure distances to things like globular clusters, but the Cepheids are good all the way out to nearby galaxies. And we're going to watch this one here, and that explains that. I'm going to add that video in later. Here is the first galaxy that we measured the distance to. This was done by Edwin Hubble in the 1920s. And there it is, that little smudge. And you can actually see that with the naked eye. I've seen it myself out in an observatory in Arizona. But anywhere you can go where it's dark enough and you know where to look, that little smudge is kind of our sister galaxy. It is absolutely beautiful, as you can see there. It's huge. It's actually larger than our Milky Way galaxy. It's the biggest galaxy in our neighborhood. And as you can see, these are actually little dwarf galaxies that orbit it. So it has some companions. Okay. So The RR Lyraes I mentioned were used for globular clusters. So a guy named Harlow Shapley, about 100 years ago in the early 1900s, was able to plot out where all the globular clusters were located. And thanks to that, he came up with some very big discoveries, the biggest of which is here's the galactic center. If you look at the picture, here's the sun, and the center of those globular clusters then is the center of our galaxy. And we're really far away, 28,000 light years away. So that showed us that we are not close to the center of our galaxy. Just like we learned in the 1600s, we're not the center of our solar system. Thanks to measuring the distances to globular clusters, we found out, hey, we're nowhere close to the center of our galaxy either. And we also learned that the Milky Way was a lot bigger than originally thought. We now think our galaxy is 100,000 light years across. Let that sink in. A beam of light would take 100,000 years to go from one side of our galaxy to the other. It's just, you can't fathom that. It's just unbelievably large. Here is a globular cluster, just to remind you what they look like. And that was the key to measuring the size of our galaxy and our place in the galaxy. And so next time we'll learn a little bit more here about measuring the Milky Way.